Hi, this is Laura Spinella from NREL, and I want to thank you all for tuning into the workshop and tuning into my talk today. Today I'll be presenting our reliability assessment for the low temperature solders that are used in multi-wire interconnects, such as the Smart Wire Connect technology from Meyer Burger. So how do we approach new PV technologies? We all want good renewable technologies to succeed and to advance renewable energy. But how can we say that these new technologies are good? You might say, why not just apply the developed standards that we have? So the current standards were more or less empirically developed for a typical module construction, which may not apply to some of these emerging technologies. And because of that, the accelerated testing may not activate all the field relevant failure modes in these technologies, or the testing could activate failure modes that aren't apparent in the field, which would lead to misleading results and possibly disqualifying a good technology. So in this talk, we'll be using multi-wire as an example of how to approach an emerging technology. And we know that multi-wire uses a different type of solder, and it uses wires instead of bus bars, uses distinct processing. We know that these new solders have different properties from the conventional tin lead solders that are being used. So we would expect there's a good possibility that multi-wire might have distinct failure modes, or at least distinct failure rates. So multi-wire interconnections use a low temperature lead-free solder, and that solder coats the wires. The wires are then embedded in a polymer foil, and the foil is aligned on the cells prior to lamination. And then during lamination is when the interconnects are formed due to having this low temperature solder in place. And multi-wire modules are already in production, and there's a lot of benefits to using multi-wire interconnects. One of the large ones is decreased thermal stresses, so you don't have that localized stress from soldering, and it's much lower stresses overall, which can reduce the risk of cell cracking and makes it compatible for technologies that are more thermally sensitive, like heterojunction. And there's some other benefits like interconnect redundancy, some performance improvement, and they're sustainable because it's lead-free and it's supposed to, typically it reduces the silver consumption to use this technology. And so there's two different approaches that we're taking in studying these solders in the multi-wire. The first is to look at the thermomechanical fatigue, which is conventionally the way most solders will fail. And then the second approach is to look at the mechanical wear of the contacts. And so we'll get to that in the second part. In the first part here, I'll start by discussing the thermomechanical fatigue cracking. So the samples for the thermomechanical fatigue were designed with a high thermal expansion mismatch in order to accelerate the damage in the solder. So we have copper cylinders that are soldered to DBC substrates. And then these substrates are thermally cycled. We used 3 different thermal cycles from more intense to least intense, where TC1 is fast ramp and a high temperature differential. So, and these 3 were used so that we could see how the damage in the solder is accelerated with respect to the cycling temperature and the cycling frequency. And there were 4 solders that we looked at throughout this whole study, one being the conventional tin lead for comparison. The second is indium tin, which was used in the earliest generations of multi-wire. However, it's pretty costly. And so we also looked at tin bismuth, which is apparently more popular at this point. So we looked at 2 different tin bismuth alloys as well. The cracking was measured via CSAM, or via acoustic microscopy. And so this is looking through the bottom of the joint. And we can see that at 0 thermal cycles, we just have the initial voids. By 500 thermal cycles, it's pretty clear we can see that crack moving in from the left. And then by 1,000 thermal cycles, that crack has grown from the left side there. So the CSAM allows us to quantify the crack area as it progresses over the thermal cycles. And then we choose a failure criterion in order to look at some of the statistical analysis. So these are the normal probability plots that we're using. The y-axis is the cumulative probability of failure, while the x-axis is the cycles to failure. And so these are the plots for tin lead and indium tin, where both are showing the same trend, where the damage is accelerated with increasing temperature and increasing cycling frequency. And so this is what we already know about tin lead, that especially with increasing temperature, you can increase the damage pretty quickly. And so we see that indium tin has a similar acceleration behavior to tin lead. It might be a little different in the exact equivalency to the field, but the trend is the same, which means that the thermomechanical fatigue of indium tin can be accelerated through standard thermal cycling protocols. However, on the other hand, for the tin bismuth alloys, what we found is that the damage is not accelerated when you're increasing temperature and cycling frequency, meaning that the highest lifetimes were observed for the most intense thermal cycle. And this is a really significant result because this indicates that the standard thermal cycling protocols could produce misleading results. And that is more clearly demonstrated in these plots, where on the left we have all the solders compared under the most intense thermal cycle, under TC1. And so under this thermal cycle, we see that the low T solders appear to outperform the tin lead, which would be great news for the low T solders if you were only looking at this one thermal cycle. However, on the right, we see under the least intense thermal cycle, under TC3, we see that the tin bismuth alloys are being outperformed by an order of magnitude. So this is showing that if we don't understand the acceleration behavior of the materials, we may just look at one thermal cycle or one test result and jump to conclusions that may not be true, because this indicates that at field conditions, the tin bismuth alloys would be expected to have pretty poor thermomechanical fatigue resistance. And that's because they're not accelerating. So you're comparing accelerated damage under an accelerated test, you're comparing accelerated damage in the tin lead to the tin bismuth alloys, where the damage is really not accelerated. However, this doesn't mean that we should throw out the multi-wire technologies. There are some reasons why we suspect that thermomechanical fatigue may not be the primary failure mode for multi-wire technologies using these tin bismuth alloys. And one of those reasons is that the IEC 61215 prescribes even lower thermal cycling frequencies than we're using here. But the multi-wire modules pass those tests, and in literature pass even more thermal cycling tests using the tin bismuth alloys. So this would indicate that there is some other mechanism that is allowing for good electrical contact, despite cracking in that joint or other weaknesses in the solder. It's a pretty early technology, so we don't have a lot of results, but we know that early field failures haven't been reported, and that early field results look pretty good. And so when we look at the unique processing and the unique geometry of the multi-wire technology, we can see that it is possible that the primary electrical contact method is through mechanical contacting, not just through metallurgical contacting, because we have these wires that are pressed to the cell with the polymer foil, and you have the redundancy. It's just a very different technology than a conventional panel. So this is why we pivoted to looking at mechanical wear out. So we tested the wear out using dynamic mechanical loading. We tested two different multi-wire modules, one being an earlier generation that used indium tin as its solder. The second being a more state-of-the-art multi-wire module that used the tin bismuth alloys. And so during the DML, we also had a conductance measurement set up, as well as taking EL and IV and then doing coring afterwards. So for the early gen multi-wire module that used indium tin, we saw a pretty clear drop in the conductance in the first 1,000 cycles, and then around 2,000 cycles, a similar drop, and then a pretty significant drop in the conductance at around 4,000 cycles. So there's clearly some damage occurring during the DML. The damage was most apparent in the EL at high currents and at high temperatures, which indicates it's more of a resistive issue. So something with the metallization, the contacts, the interconnects. Most of the damage was not linked to broken wires between the cells. We looked at that. And so we are attributing most of the damage in that case to degraded contacts. So some wear out happening at the contacts in these modules. On the flip side, the state-of-the-art module that was using tin bismuth, we saw pretty much no degradation. These modules had 2 crossbars on the back that were providing mechanical support. So we removed those crossbars to have a better comparison to the earlier gen module that didn't have crossbars. However, with or without crossbars, we didn't see any degradation in the conductance. We didn't see degradation in the EL or in the maximum power output. So this is an interesting result showing that for the mechanical failure, we might expect the indium tin to be more susceptible. And so in order to test that more scientifically and look at how the properties of these solders might be impacting the results for the modules, we worked with C.S. Zhang, who's the AFM expert at NREL, and used scratch testing in order to look at the wear. And so wear is represented as the volume of material lost in terms of the force applied and the length over which that force is applied. And so then there's a wear coefficient K, and so we're using this wear parameter K over 3H to compare how these different materials would wear under the same loading conditions. And that's the results we see here on the right, where the indium tin has the highest wear parameter, meaning it is going to wear the most out of these solders, and the tin bismuth has a much lower wear parameter. So this means that indium tin would be much more susceptible to abrasive wear out than the tin bismuth. And that is what we see in the DML results, where the module using indium tin did show damage of the contacts over thousands of cycles of DML when the tin bismuth, the module using tin bismuth, didn't show any damage of the contacts. So in conclusion, this multi-wire reliability assessment highlights several important considerations when we're thinking about how to test and certify the reliability of new and emerging PV technologies. So the first is considering the fundamental material properties. So our results indicate that tin bismuth alloys on the whole demonstrate poor thermomechanical fatigue resistance at field conditions, and that the damage isn't really accelerated through the conventional thermal cycling protocols. And then secondly, the material properties show that the indium tin is more susceptible to abrasive wear out than the tin bismuth. And so both of these are interesting results because they're different than what we expect from conventional tin lead, which means that we may need to adjust our accelerated testing protocols for these new materials. And then the second thing is module construction, where the unique processing and the interconnect geometry of multi-wire likely allow for a different contacting method. They likely allow for mechanical contacting rather than just metallurgical contacting. And so this is also distinct from what we see in conventional panels, and also may indicate that we need to adjust our accelerated testing protocols for these types of modules. And then lastly, we'd like to correlate these types of results to what we see in the field. And so we know that we haven't seen early field failures. And so we have a couple of multi-wire modules that were just deployed at NREL, and we'll be monitoring those to see if we can identify what the field failure modes are in order to tie all the results together. And so the overall message here is that if you're changing materials, if you're changing construction, you may need to reassess how you test the reliability of those new and emerging technologies so that we can demonstrate that they are useful and they are good. Thank you.